Hey everyone, welcome back to The Explainer. Today we're jumping right into what is, honestly, one of the most incredible engineering puzzles out there in modern manufacturing. We are looking at a process where temperature and time hold literally all the power. They alone dictate whether you get an absolute success or a total catastrophic failure. Yep, we're talking about metal casting.
I mean, just think about that for a second. How do you actually control a liquid that's thousands of degrees hot, incredibly volatile, and desperately, almost aggressively wants to turn back into a solid? That right there is the sheer physical challenge of casting. You're basically fighting the laws of thermodynamics, trying to force molten metal into these really complex geometric shapes before it freezes up on you. It is a high-stakes race against the clock.
All right, let's dive into this. To see how engineers actually win this race, we're going to look at four crucial stages: the perfect pour, the fluidity factor, the solidification countdown, and finally, surviving the shrink.
Okay, Section 1, the perfect pour, beating the freeze.
So getting the metal into the mold is a seriously delicate operation. We've got a classic rule of three here. If you don't perfectly control your pouring temperature, your pouring rate, and your turbulence, well, those become your three villains. They will instantly ruin your cast. Let's break them down.
First up is pouring temperature, and the absolute key concept to understand here is superheat. Think of superheat as your safety buffer. It's basically the temperature difference between the metal, the exact moment it's poured, and its actual melting point. You know, the exact moment freezing begins. It's a measure of the extra heat that has to be bled off before solidification kicks in. You need enough of a buffer to actually fill the mold completely, but not so much that you literally melt or damage the mold itself.
Now, what's really interesting here is that finding the perfect pouring rate is a total Goldilocks scenario. It has to be just right. If your volumetric pouring rate is too slow, the metal chills. It loses all that superheat way too fast and freezes before it even finishes filling the cavity. But if you go too fast and your rate is excessive, well, you trigger violent turbulence. And that leads us straight to our third villain. Turbulence is absolutely the enemy of a smooth, high-quality cast. Instead of flowing in this nice, streamlined, laminar way, the liquid metal gets super agitated and erratic. So why is that bad? Well, three main reasons. First, it accelerates the formation of metal oxides, which get trapped inside and weaken the final part. Second, it promotes the absorption of unwanted gases, leaving you with microscopic bubbles or voids. And third, it severely aggravates mold erosion. The violent impact of the liquid metal literally wears away the interior surfaces of your mold. Not good. Moving right along to Section 2, the fluidity factor, the liquid race. All right, so once the metal is actually moving inside the mold, the whole game is about fluidity. As a quick refresher, fluidity is just the inverse of viscosity. A metal with high fluidity flows really easily, kind of like water, but a metal with low fluidity, so high viscosity, drags and resists movement. It's much more like trying to pour thick, cold honey. Obviously, you desperately want that water-like fluidity so you can fill those complex molds before the freeze hits. And to actually test this out in the real world, engineers use the standard spiral mold test. It's really cool. Molten metal is poured into a center cup and then just allowed to literally race through this outward winding spiral track. It flows as far as it possibly can until it finally loses its heat and freezes solid right there in the channel.
Which leads us to a very simple, elegant conclusion. A longer cast spiral means greater fluidity of the molten metal. The physical distance the metal actually manages to travel to that spiral is your ultimate scoreboard. It tells you exactly what kind of time and maneuverability you're really working with.
That brings us to Section 3, the solidification countdown. Math meets metal. So this is the exact moment where the dynamic, messy pour turns into a strict mathematical countdown. Once the metal comes to rest inside the mold, geometry takes over. The total time it takes for that liquid to turn completely solid strictly depends on the size and the shape of the casting.
We can actually predict this down to the second using Cherevanov's rule. Now, while there's a constant in there for the mold material itself, the real star of the show is that fraction right in the parentheses, V over A, volume divided by surface area. Those two variables are the absolute key players dictating your countdown clock.
Let's turn that math into a simple geometry race. Check out these three shapes: a cuboid, a cylinder, and a sphere. If you compare shapes that have relatively similar volumes, just look at how wildly the surface areas differ. The cuboid has a massive surface area of 22, meaning it bleeds off its heat incredibly fast. But the cylinder and the sphere? Their surface areas are much lower relative to their volume,
giving them a higher volume-to-area ratio of 0.33. They are the clear, undeniable winners when it comes to retaining heat.
So the crucial takeaway here is this. A higher volume-to-surface area ratio cools much, much slower. Minimizing surface area relative to your volume is the ultimate secret weapon for buying more time before the metal freezes. And engineers actually exploit this exact mathematical principle to pull off a pretty brilliant trick.
They outsmart the freeze by using something called risers. A riser is basically a sacrificial pool of extra molten metal that's connected to the main cavity. By designing the riser to be a really thick shape, like a cylinder, it naturally has a larger volume-to-area ratio than the main casting. And because of Trevornov's rule, we know the main casting is going to solidify first. As it shrinks down, it simply draws still liquid metal from the hotter riser to fill in any gaps, ensuring you get a flawless final product.
Okay, finally, Section 4, Surviving the Shrink, the final boss.
So why does the metal shrink so aggressively in the first place? Well, it's an inevitable physical reality, and a cast part has to survive 3 distinct phases of it, chronologically. First up is liquid contraction, which happens as the superheat bleeds off just prior to freezing. Then you have solidification shrinkage. That's a sudden, pretty significant contraction right during the actual phase change from liquid to solid. And lastly, thermal contraction, where the now solid part just keeps shrinking as it cools all the way down to room temperature. Your mold and your risers must be precisely designed to accommodate every single millimeter of the shrinkage.
And, as a truly fascinating side note on the life cycle of these metals, the effects of heat don't actually stop once the casting leaves the factory floor. If certain carbon steels are subjected to extreme heat for long periods of time in the field, say sitting between 450 and 600 degrees Celsius, they undergo this weird metallurgical change called graphitization. The structural carbides in the steel literally break down into small, weak patches of graphite and iron. So yeah, heat remains a highly destructive force long, long after the casting is solid. Which leaves us with a pretty thrilling thought to wrap up on. Metal casting is this incredibly delicate mathematical dance with fluid dynamics, extreme heat, and geometric contraction. As we push the absolute limits of manufacturing, building lighter, stronger, and far more complex geometries for aerospace and beyond, how will future designers continue to outsmart the unforgiving physics of shrinkage and freezing to cast even more impossible shapes? It's a spectacular field of engineering, and one that just never stops innovating. Thanks for joining me on this explainer, and definitely keep questioning how the world around you is made. Catch you next time.